This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. SE Radio listeners, we want to hear from you. Please visit se-radio.net/survey to share a little information about your professional interests and listening habits. It takes less than 2 minutes to help us continue to make SE Radio even better. Your responses to the survey are completely confidential. That's se-radio.net/survey. Thanks for your support of the show. We look forward to hearing from you soon.
Welcome to Software Engineering Radio. I'm your host, Akshay Manchale. My guest today is Mike Del Balso, and we'll be talking about feature stores. Mike is the co-founder of Tecton, where he is focused on building next-generation data infrastructure for operational machine learning. Before Tecton, Mike was the PM lead for Uber Michelangelo machine learning platform. Prior to Uber, he was a product manager at Google, where he managed the core ML systems that power their search ads business. Mike, welcome to the show.
Hey, thank you for having me.
Awesome. So let's start with some context for the rest of the episode. Can you briefly describe what a feature store is?
Yeah, so a feature store, we think of it kind of like a data platform to support the data flows that are needed in a production machine learning application. So machine learning applications have two components to them. Of course, there's models, and there are data pipelines that feed the right input signals to those models. So the models can use that data to make a prediction. And there's a lot of operational challenges around both the models and the data. We need to organize these models and data pipelines. We need to productionize and serve them and monitor them. And so those signals, those data pipelines that are part of a machine learning application, those data inputs to a model are called features. And so the term feature store refers to a piece of infrastructure that organizes the data pipelines for a machine learning application and provides some of the implementation for productionizing these data pipelines and using them in a customer-facing ML application, say for a live recommendation service or a live fraud detection service.
Let's take that example of, say, a live recommendation service. And can you explain just the terminology of what makes a feature, what is a model, those components? Can you explain that in the context of, say, that live recommendation service?
Great. So if we're an e-commerce company and we want to show a recommendation to the user who's browsing the website, we want to recommend an item for them that they may also want to buy, for example. We may have just intuitively a variety of signals, a variety of things that influence what we think this user might be interested in, right? Maybe this user previously was looking at, women's fashion. So we know that maybe they're probably interested in items related to women's fashion. But maybe also today in the session that they were on their website today, they were clicking around a lot, specifically in pants. And so maybe that kind of gives us another clue that maybe they're looking for women's pants. And they also may have just typed into a search box capris or something like that. And so that's another signal that's actually a very high intent user signal from there, which is kind of something that's delivered in real time. It's not about looking at the history of the user. So point is, all of these signals, all this information we can collect about a user for a given kind of decision we want to make, is we can all use this to kind of feed into a decision-making process. And we can do that intuitively as humans. It's kind of obvious how to think about this stuff, but it's not always clear how to develop a software system to generate that recommendation and an accurate recommendation. And not just to develop such a system, but to also rely your business on that. If you have a website that's making money, how do you make this a reliable software application? How do you have reliable predictions that are tuned to be high quality predictions that lead to more sales, for example? And so high quality recommendations. So the parts there are, we need a machine learning model, which is something that is the system that takes these data inputs in and makes the decision of, hey, this is the item we should recommend in this instance. And that machine learning model is trained. So it learns from a variety of historical examples. So we would like learn this machine learning model from a variety of historical examples of impressions that the user has seen from previous recommendations, and also data about whether they clicked those recommendations or not. And that's called the training data set. And that's what a machine learning model is built on. It looks at all these historical examples. We run those examples through what's called a training algorithm, and that outputs basically a decision making system that can act on, it's almost like a transformation that acts on the input, some input data, and can output which item we want to recommend. And as you build that model, you can configure the training algorithm to optimize for different things. And so we may configure it to optimize for likely like the highest click-through rate. Like we want to recommend the object, maybe the piece of like the fashion article of clothing that is the most likely thing that we think someone will click on, and that will correlate quite well to us increasing our revenue if we have higher quality recommendations. So that model depends on having these signals that we just thought about and we just talked about intuitively, right? Like, what does this person typically search for, and what did they type in the search box right now? The model needs that data in a very structured format, in a very specific format for it to be able to act on it, and for it to be able to interpret that data and use for its decision making process. And the data, and so there's special data pipelines that are set up that one has to build while they're building a machine learning application to both generate that historical training data set for a model to be trained on, and also to generate the latest versions of all of these signals when a model is making predictions. So when we're building a model, we need to look through and process our logs data to come up with, here's all the times someone saw a recommendation before, this is what we knew about them, these are the signals that we knew at that point in time in the past. So this is kind of like historical feature values. At this time in the past, someone had just searched for men's pants, someone had just searched for a hat, something like that, and then this is what we recommended, and then this is whether or not that user clicked on the recommendation or not. And we compile all of that, and that becomes the training data set. And it's a real data process. There's a lot of people put a lot of work into the data process for compiling that data set. And that's what you often hear ML people say, like, 90% of doing machine learning is data cleaning, data preparation. That's what that work is, to prepare that data set. And then when you want to use that model, and now we're getting into the deployment, we've built the prototype at least. We've come up with the model we want. We want to productionize that. There's a similar set of data pipelines that are used to deliver those data signals to the model at production time, and those have to be real-time pipelines that represent the current state of those features for the current session, the current user, their current context. Does that make sense?
Yeah, the second part of that is what you mean by operationalizing your machine learning model. So, can you walk through what the general challenges are in terms of taking this recommendation system that I may have built with training data, test data, with a set of features, and then operationalizing that in actual production system? So, what is that? What are the challenges there?
Yeah, I think the biggest challenges are actually that there's just not one way to do this. We're kind of it's kind of a new thing for a lot of companies that are even software companies. They've been building software and depending on it for that being their product for a long time. But adopting machine learning is kind of a new challenge for them, and so that brings with it some different development processes. There's different ways to productionize that I'll talk about, but there's also different ways to monitor and maintain these systems. There's different things that one has to track to allow them to identify issues, to allow them to debug these systems and address kind of like outages as well. So when someone thinks about like what is unique about or what are unique challenges of building and deploying ML systems compared to typical software? There's a really interesting kind of difference here, is that we're not just compiling a single binary and deploying a binary. We're compiling something that has a very specific external dependencies on data pipelines, on data resources that are always being updated. So when people talk about like, hey, I'm deploying my machine learning system, it's your machine learning system is both the model artifact, but it's also these data dependencies that need to be maintained, and they are always changing. They're very dynamic. They, that's data that's always being processed, and you know, deploying a simple machine learning system is not as big of a challenge as deploying some of the more complicated or sophisticated ML systems that are used for more like higher value ML use cases. So they're very important to that business. So think about like a pricing system for a insurance company, or think about like surge pricing for Uber, or the estimated time of arrival for Uber, or even an estimated click-through rate for Google, where Google's trying to, make sure they show you ads that you would click on, right? They don't want to show you ads you're not going to click on. And a lot of these use cases they're very valuable, and high accuracy is very important for these use cases, and that motivates finding as many ways as possible to bring in additional signal to make a model more accurate. So the more fresh signals, the more context we can get, the better kind of information and data we can get about what's going on right now. That is kind of obvious, like it's intuitive for us as humans, that we can feed into a model. More likely, the better that model will be, and that will lead to some business impact. So in practice, what happens is these ML applications that are quite meaningful, that have real economic impact, like some of the ones I just mentioned, there's a really complicated whole nest of data pipelines, different services that are built to support these, to process all the different types of data that the business is seeing, that the business has, and translate that data, extract the signal, aggregate that data, mix and match this data, and extract the signal and convert it to a format that's consumable by the model, and deliver it in real time to a model. So some of these signals are computed in real time. Some of them are, batch signals, stuff like that, like we just talked about. Some of them are based on streaming infrastructure on Kafka. And some of the biggest challenges for these teams are just keeping all of these tools up and running. And if you're a data scientist, you're not going to be an expert in all of these different technologies. And so that's why, like, a lot of these more sophisticated ML, more valuable ML use cases, they have huge teams of engineers supporting them. And that makes ML kind of like not accessible, like meaningful ML not accessible for teams that cannot staff up giant engineering teams.
Yeah, so you do have like data engineers who can actually bring the idea that might be conceived by a data scientist into reality by building these pipelines. And if I'm hearing you right, that you're saying the quality of signal also depends on various sources and various characteristics that are in different places. You mentioned Kafka, so you could have streaming data, you could have a data warehouse. So how are all of these things usually connected? Is there some example that you can share which drives the point about the complexity involved in building these data pipelines from different sources to actually operationalize a machine learning model?
Yeah, totally. Well, so there's kind of the, like, how are they usually connected for, a, a lot of companies that are practically getting started with this today, and then there's how are these things connected in the most efficient way, or in the way that companies that are successful are doing it. And so let's just take
the other end of it.
yeah, let's
Yeah.
just take a concrete example, right? Like we had this machine learning model at Uber, which would estimate how long it would take your Uber Eats order to be ready for you, right? And so there's a variety of signals, but let's just talk about two of them that could become predictive features for your machine learning model. One is, how long does it normally take for them to prepare a dish? Super simple. that you can just calculate once a week, once a month. You can calculate it even once, and just make sure that that's always available to pass into the model. That's good, but sometimes, sometimes it's a busy time of day, or sometimes, a restaurant is uncharacteristically busy, like it just got some spike of orders. And so a second type of signal, which is slightly more complicated, is one that's based on some recent data. So it's like you can think of how many orders did this restaurant get in the past 30 minutes, and how does that number compare to what they normally get in a 30-minute period? And that can give us a sign of like, hey, is this like really really busy right now? And if so, then they're probably going to take longer. That's hard to compute in a data warehouse, right? A data warehouse may not have all of that real time, all the data from the past 30 minutes being available in it, and it's not meant for kind of like faster operations like that. So at a company like Uber, what we would do is we have all of these order events be populated onto a Kafka stream, and then we have some streaming aggregation jobs that are reading these Kafka streams, aggregating these data to the number of orders per restaurant, and in a time in an aggregation window that's like the last 30 minutes, always updated in real time, so that when we need to make a prediction for, hey, this restaurant, how long is it going to take to have that meal prepared for you, that signal is available immediately for that model to make that prediction. And so, but your question is like, how do people like practically, like if you're just like a small company or a data scientist, how do you do this?
Yeah,
The
your
answer
first model.
the
How do you
answer is
get that?
like
Yeah.
realistically you don't. Like that's what was happening at Uber when we started, is just like a lot of this stuff is hard. And so at Uber, and we see this in a lot of other companies right now, they're kind of in like one of three situations. So situation one is it's a super important use case for the business, and like the business needs this ML model to work no matter what. And so what they do in those cases is they put a bunch of engineers on it. So the data scientist comes up with some prototype, and then they hand it off completely to an engineering team, and the engineering team takes maybe like a notebook of Python code that they may not understand fully from the data scientist, and then they productionize it, quote unquote productionize it. And that means rewriting some data pipelines in a variety of different more engineering centric technologies. It means building production services, building the right monitoring, a lot of custom work for a specific. It's basically building like a custom engineering microservice to make these predictions. These systems tend to be quite brittle, very expensive because you need to staff a whole engineering team on them, and hard to update. Right? If you're a data scientist, you got to go through the engineer every single time. So that's a challenge with those. And when we started the ML team at Uber a couple of years ago, there was only a few instances of teams having gone through that flow successfully, just because it's so expensive on the engineering side. The second situation is the data scientist comes up with the prototype, and then they think, okay, this is great. Like I found the model I want to use. I brought together some of the data I wanted to use, and I kind of simulated what the signals I want to have in that model in my Python environment. Now, how do I productionize it? And then there's crickets, and then nobody knows how to productionize it. There's not a path to do that. Like there's not the engineers there to rebuild this whole thing in the production or the operational environment. And then the data science project kind of just gets blocked there. And then the data scientist has other things people are asking them for, and then she'll go off and work on some other projects, and that project will kind of die. The third situation, which is very, very common, is people don't start on these projects in the first place. Data scientists will know, hey, I have actually no path to production. There's no way I can build a real-time ML system that's productionized anyway. So I'm just going to work on this other problem that we have in the company, BI problem. I'm going to make some dashboards or something like that. That's very common, both from a data science decision perspective, where they think, I don't have a path to production, so why am I going to even bother? And also from the engineering leadership perspective, where they think, wow, if I put my engineers on this, that's so expensive for us from an engineering cost perspective per ML use case, that I don't even want to support another ML use case. It's just going to incur more technical debt for us, and it's just going to be more stuff that I have to support. It's not worth it for me. So I think the goal right now for the industry is how do we, one, build that path to production for data scientists, like make it possible for them to get their stuff into production, and two, lower the cost, the engineering cost, so the engineering teams don't see supporting ML as a burden. How do we help a given set of engineers scale to support more and more data scientists over time?
And just to be clear, one of the things that you mentioned, the data scientist just goes off and builds a dashboard. That is kind of like the classic analytical machine learning sort of a thing, right? That's very different from what you're trying to say with respect to actually having models in production. So can you just briefly describe what that is, and then we'll jump into how to solve this whole problem and this challenge of agility.
Yeah, great question. So we started talking about, and this kind of started a couple years ago, but we started really recognizing that there's a big difference in the success and the cost of an ML use case depending on who is the consumer of that use case. So when you think about like, hey, this is a machine learning project in my company, it tends to be that if the machine learning project, if its purpose is for some internal consumption, something like some analytics purpose, or some, let's extract some patterns from our data so we can look at it and make a decision, or let's do a forecasting of our sales, those tend to be a lot less costly than the other types of machine learning projects, which what we call operational ML. So the first we call analytic ML, second we call operational ML. The operational ML is use cases that are just in production. They power your product, right? They're powering your customer experience. These are things that some of the use cases we just talked about, right? Like the ETA system at Uber, or a pricing system that powers an insurance company's website, right? Stuff where if it goes down, your product is going to be broken, your business is going to be broken, your customers are going to notice. That requires a different tier of operationalization, a different tier of productionization, and when a machine learning project, when a data scientist switches from moving from analytical machine learning, where kind of they're in control and they are the end-to-end owners of these systems, and the stakes, frankly, are a lot lower, to operational machine learning projects, where things have SLAs. There's a lot more engineering requirements. There's real business impact if something doesn't perform, or if something's not behaving correctly. That's a real challenge for data scientists, and that's where they begin really needing engineering support. And so those types of operational use cases, operational ML, is actually like what we focus on at Tecton. How do we help people put machine learning into production and build their products on the different machine learning applications that they're building?
Okay, great. So now let's talk about feature stores, right? So you mentioned they're used to operationalize your machine learning models. So can you go deeper into how that actually solves this whole problem of operationalizing a machine learning model?
Great. Yeah. So the fundamental, like the big cost that we just talked about putting an operational machine learning model into production, is that a lot of engineering resources are needed to help a data scientist rebuild their model in production, rebuild their data pipelines in production. And so at a high level, what a feature store does is it resolves that duplication. So it provides a way for a data scientist to define the data signals, the features that they need in their model. And when they define that at the training stage, at the stage when they're building their model and they're just exploring, what models they want, and they're in that exploration phase, when they define those features are defined in the feature store, and the feature store handles the productionization of them. So an engineering team is not needed for the productionization of these features. So what that does is it reduces the need for data science teams and engineering teams to collaborate within the core iteration loop for data science. And it enables data scientists to contribute to the production model. There's no longer this like throw it over the wall to a data engineer. The data scientist gets to own their work. They can deploy to production on their own, and they become the owners of the data science app, the whole data science model, all the way through to production. And this actually kind of changes like what their responsibilities are too, right? Like they're no longer the person who just doesn't really know exactly what's going on with the production model. They're the owners of the production model. And so the feature store is the management platform and the platform that runs these pipelines in production. So the workflow that we enable for a data scientist is the ability to define features declaratively, and then register those features centrally in the feature store, and then have the feature store essentially be this catalog of trusted signals that are usable by machine learning applications during the development and process and production. And so then those features can be used to generate training data sets when a data scientist is developing to build models. And those features can also be queried by model services, prediction services, and from the production environment to get the latest values of these features. So it's kind of automating a lot of the data engineering work in productionizing machine learning applications.
SE Radio listeners, we want to hear from you. Please visit se-radio.net/survey to share a little information about your professional interests and listening habits. It takes less than 2 minutes to help us continue to make SE Radio even better. Your responses to the survey are completely confidential. That's se-radio.net/survey. Thanks for your support of the show. We look forward to hearing from you soon.
This sounds like how databases kind of changed way back, or how you look at your data and organize and actually query by having a declarative way to query and look at your data, right? So if I were a data scientist, maybe in the past I had a CSV file that I would just run through a Jupyter notebook or something to look at the model that works best. CSV file is having the data exported from various different sources. So how does a feature store kind of fit into this, where it's taking you close to the data directly by bringing that pipeline to you in some way, by saying, oh yeah, this is what I care about, or this is what I want? How does a feature store solve that?
Let's do like the juxtaposition of the before and after, right? So just for training a model, let's do training models and then serving models, right? Like development and productionization. So just for training models, let's imagine you're making the second model in your company. So there actually already is, you're making the second fraud detection model. There's already a fraud detection model in your company. So today what you do is, or maybe like in the past in your example, what you do is connect to various databases, figure out which data you might need, download them to maybe your local machine, open up those data exports in a Python environment, clean up the data, try to join them together. You got to bring all this data together in one data frame, and then run transformations on this data to aggregate this data, to extract out. It's called featureizing and feature engineering, to extract out the relevant signals for the machine learning model that you want to build, and train a model, and then see if your model is accurate, and then repeat. And one really tough thing here also is what you need to do is, when you're building your training data set, you have to be very careful about something that's called data leakage and in machine learning, where you don't want to have information about the future leak into your historical data. And so a really hard challenge for data scientists during this process also is, how do I construct my training data sets when I have all this exported data in such a way where, yes, I'm transforming this data into feature values with different types of data transformations, but how do I do it in a way that tells me what that feature value was at that point in time, and not just what that feature value is now? Because the model needs to be able to train on what the model would have known at that time when we was making a prediction in the past. So there's a lot of steps there, right? Now let's talk about if for some of our data scientists who are using feature stores for their model training phase. So the first thing to know is, if this is your second model in the company, that means a lot of the features that are already available, that have already been built in your organization, are already available in a standardized way for training purposes. So if I'm building a second fraud model, I can go and say, hey, give me all of the user features. This could be hundreds or thousands of features. Give me all of the transaction features. And so maybe I'm already hot starting my data science project with 1,000 really high quality features, which is really nice. But I also tend to, for every new use case, have to build a bunch of new features as well. And so I will be defining some pretty straightforward feature definitions in a which is basically like writing some data transformations into Tecton framework, a feature store framework that that essentially defines a data pipeline. So I'm going to define a data pipeline. And then when I'm trying to I'm trying to generate that training data set, right? So I register the data pipeline into the feature store, and now I want to generate a training data set. What Tecton and feature stores generally should do for the data scientists is that they handle all of that historical backfilling of feature values. They handle joining all of the feature values together as of specific points in time. So they really like protect against a lot of these really nasty time issues with data that data scientists always grapple with and sometimes don't realize. They're really easy to make some errors here, and generate that training data set for the data scientist. So the key points is that it allows data scientists to reuse a lot of their work and hot start new efforts, and then also like simplify a lot of the process of bringing this data together. But some of the larger benefits are really felt at times when now we're productionizing things, because in the status quo today, you go to the data scientist goes to the engineer and says, "All right, cool, I found my model. Let's productionize this." And what does the engineer say? Okay, so like, what did you build, and what should I build? And you say, okay, so I have this CSV that I kind of downloaded from a couple of databases, and I wrote this Python script to generate my model. So figure it out, And the data engineer then has to understand, okay, how was that CSV created? Because that data engineer has to not just read from that CSV, but read from those original data sources, so they can provide up-to-date data. They can always use the freshest data to have updated predictions, right? So they have to rebuild these data pipelines and connect to the original data sources and re-implement all of the data transformations that you had defined in your Python notebook. This is a painful process, and it obviously sounds painful, but the problem is pretty tricky for larger organizations, where if we talk to some of our kind of larger enterprise clients, they were having challenges where these challenges plus governance and compliance workflows that they deal with in their large organizations means this stage can take 6 or 12 months. And what they really like about the concept of a feature store is all of that is just automated for them. Actually, this problem was solved during the development time when I defined my feature and registered my feature into the feature store back when I was training a model. That set up the production data pipeline automatically. So now when it's time to productionize the model, all of the data pipeline productionization is already done, and the data engineer is not needed in that loop. So that's like the real area for simplification here.
Yeah, that sounds great. Let's take Tecton itself as an example. And can you explain how it connects to various data sources and then prepares this feature that a data scientist actually cares about?
So Tecton has a couple of components to it. So at a high level, Tecton has a few different elements. It has transformations, where it basically, you can think of that as like the data pipelines that it runs. It has a storage layer, and it has online serving, or it has a serving layer. And so each of these elements is configured by a feature definition. So a data scientist, the whole goal is for a data scientist to be able to self-serve, autonomously define, this is the signal that my model needs. And they should describe that signal. They should be able to describe that feature. And Tecton translates that into a configuration for the data pipelines, for the storage and the data management layer, and then for the online serving. So that configures both the development pipeline and the production pipeline. And so if you in Tecton define, say, a signal that is, let's just choose one of the examples we just talked about, like how many orders did this restaurant get? Did a restaurant get in the past 30 minutes, right? That's a very common type of feature pipeline that someone would want in their feature store. What Tecton does is it takes that definition that you define. So you define a SQL query, or you may configure something in our library through our DSL to specify like a special type of aggregation, but basically like the definition of that transformation. And then you also write some of the metadata, like or some specific configuration code that would say, hey, I need this available online. This is how I want this signal backfilled. Like, how far back in time might I want to train a model using this signal? And a lot of metadata, like who's the owner for this feature, how trusted is this feature, is this an experimental feature, or is this production feature, and register that in Tecton. What Tecton does is it takes that configuration and we'll do a couple of things. One, it'll orchestrate jobs, compute jobs based on that. So it will, for example, in this streaming aggregation feature type, it will talk to, say, a Spark, your Spark cluster, and create a streaming Spark job that will connect to a Kafka pipeline with your events, and will maintain these aggregations. It'll run these aggregations and keep a up to date, past number of orders in the past 30 minutes. Those values will also be fed into Tecton's storage layer, which is kind of like what people think of as the feature store sometimes. And the storage layer is twofold. There's an offline storage layer, which is used to store all of the historical feature values for a feature. So every time there's a new version of an updated feature value, it gets stored in the offline store. And that's used for model training and model retraining later on. But that data also goes to the online store, which tends to be, we're pluggable, so we plug into different types of, there's different technologies that can implement our online store, but it tends to be a key value store that's optimized for fast retrieval, and that will only hold the latest values of these signals. And then we have a serving layer, which allows the production model, to query Tecton through a REST API and say, hey, I'm fraud model v2. This user is trying to log in right now. I need all of the signals that the feature store has, that it's prepared and it maintains fresh for fraud model v2. What are all the features for fraud model v2? And I need them within 50 milliseconds. And Tecton will deliver that to the prediction system, to the model system, which may live outside of Tecton. It can be any kind of model prediction system you have. And then that kind of enables these real-time predictions. So the kind of value proposition that we deliver to organizations that are trying to build these like complicated real-time machine learning applications is Tecton is this data platform that simplifies all of the data pipelines needed to be built and deployed for real-time ML. And it really kind of simplifies the development and productionization workflows there. So a data scientist can not only just like build a prototype, but they can run a model in production on their own as well.
Gotcha. So let's say you have multiple data scientists right now who are publishing these features in Tecton. How do they go around discovering that someone else has actually prepared this feature for me, or I can actually work off of someone else's pipeline and feature that they've already built for my model because I think this is useful?
Yeah, that's a really good question. And it's a pretty important capability of the feature store to eliminate duplication. So there's a couple of reasons why you might want to do this. There's obviously like the cost component where you just don't want two signals, that you don't want the same compute. These pipelines can be pretty expensive, right? They're heavyweight data processing jobs often. You just don't want these same things to be running again and again for no reason. But secondly, it can be confusing to people if two signals are implemented, or rather one signal is implemented twice, but slightly differently, and they have different implementations. And then that can lead to people not recognizing that they're actually implemented differently and not being careful about which one they're using. And you may train a model using one signal, but then if you're trying to make a prediction with another implementation of that same signal, if it's slightly off, your model could misbehave, and that may be hard to predict, but that will lead to model performance issues. So I'm bringing that up because there's a lot of reasons why transparency is really important. Discoverability is really important for these signals for machine learning. And so what the feature store does is provides a catalog of these production ready signals. So this is largely a knowledge management issue, but it's like, I'm a data scientist. How do I find which features are already productionized that I can use today? Literally a search interface in a web UI. I can see a catalog. I can browse, search by user, search by feature type, search by entity. So I can say, what are all the user features? What are all the item features? What are all the, in Uber we had, what are the driver features and the rider features, stuff like that. And I can also see all of a variety of pieces of metadata. So, hey, this is an experimental feature. You may not want to build your model based on this. Or this is a solid production feature that 10 other models depend on. So you're going to be fine if you depend your model on that. That kind of like visibility and discoverability is critical for allowing machine learning to scale in a company. Because once you have that, then you can kind of enable the reuse and sharing that we were talking about before. So now when I have my second machine learning model, I don't have to start from zero. I can go to the feature store and say, hey, what are the list of features that are kind of relevant for me that I might want to try out? Instead of me rebuilding 1,000 signals, let me just reuse the top 1,000 signals that my company has already put together. And maybe that's all I need to do. And maybe I can finish this machine learning project in one day instead of a couple of months.
So this is where that value of having your machine learning idea going from a year to actually get data engineers to build the pipelines can go into 2 or 3 days into production, and that's really nice. One thing you mentioned was the storage aspect of it, and is that can you elaborate on what the storage looks like? You said there's batch, there's real time, so is it going back to the source systems, or is this separate database or something? Can you talk about that?
Yeah, good point. So the way this is implemented is, there's two types of storage in a feature store. There's an offline storage layer, which holds the historical values, and the online storage layer, which holds the latest values, but it's optimized for fast retrieval. And so with Tecton, so Tecton is a cloud native solution that reuses a lot of the cloud managed services, but it's built in a very pluggable way. So Tecton doesn't have a proprietary, offline storage layer or a proprietary online key value store or anything like that. What we do is we plug into your infrastructure. So if you use Snowflake, if you use a data warehouse, we will use that data warehouse as the offline storage layer. So all of the feature data will just look like normal tables in your Snowflake or your Redshift, for example. And if you have a Redis cluster that you want to use that you already are using, your application's already connecting to for online serving, we'll use that as the online storage layer. Or we come out of the box with we will configure like a Dynamo, and we'll use Dynamo on AWS to serve this stuff. So you can think of the feature store as like a coordinating layer that brings together a lot of pieces of infrastructure that is already available on the cloud or in your account to allow your data scientists to configure these data flows that become coherent production data pipelines for machine learning applications and coordinate all these different pieces of infrastructure to enable that. Does that make sense?
Yeah, that makes a lot of sense. Yeah, I think that is where a lot of the complexity would be with data engineer trying to deliver this model to production would be, can I actually have a real-time key value store, something that gives me online data? How do I configure that? How do I maintain that? What are the needs? So I can see the simplification with, say, having a feature store, being able to plug into your infrastructure and then serve that. And that's great. So let's talk about quality aspects of it, right? So you train your model and then, you want to generate V2 of your model. How do you monitor how your V1 is doing? And how do you transition that into, say, I'm going to actually do V2 because, V1 is deteriorating in terms of what it's serving?
Yeah, I think there's a couple of questions there. The important thing that everyone who's running machine learning operationally, like running machine learning in a way that it has real business impact, a thing that's very important to do is measure the performance of your model. And that can be harder or easier depending on the use case. So in a situation, here's an example of how it's really easy. I'm going to predict I'm in a recommendation system. I'm going to predict if you're going to click on this recommendation. And immediately after, in 5 seconds from now, I'm going to know if you clicked it or you didn't click it. It's very easy for me to, and then say, calculate my accuracy, right? But if I'm predicting fraud, for example, maybe I only find out that this was a purchase made with a stolen credit card 90 days later when a credit card company comes back to me and does a chargeback or something like that. So that's a whole other data engineering challenge to, like, how do we associate that data we collect 90 days from now back with this prediction log that we made, from the past. My point is there's not just like one way to measure accuracy in a super simple way, but once you can bring that data together, then there's a couple of things that you want to do. You want to have a good sense of what the steady state performance is and track the performance of that model, but you also want to have a good sense of like how I could improve this model. And so you ask like, hey, how do I know when to retrain it? There's a couple of, there's two kinds of questions there. It's like, how do I know when my system stops operating correctly, and how do I know when I have an opportunity to improve this system? And I think practically right now, the opportunity to improve this system is driven by intuition by people. So it's, hey, we just realized we have this data source in the company that we're not using in this model, but it's it kind of makes sense that it could help us make better recommendations. So maybe we want to test it out. and let's build a prototype where we join in that kind of data and train a model on that kind of data. And sometimes in a lot of use cases, you can only really test these things out when you put them in production. So that's kind of like, how do we know how to improve the system when we're thinking about how to detect issues? That's where you have to monitor that accuracy signal over time. And if that accuracy signal decreases in some way, that might mean you need to retrain your model, or that might mean there's a challenge, there's a breakage somewhere in one of your data pipelines, or a data quality issue.
So when you say you want to retrain your model, you also mentioned sometime in the past that you store historical data in offline storage. Is that offline storage used predominantly for retraining, or is it also just because you can have batch jobs on it to serve your model?
The offline storage is used mainly for model training. So it can be for training new models or for retraining a model, right? The feature store doesn't care. It's just generating a training data set. But that's why we have these historical values in the offline store, because it allows the feature store to easily create a training data set that says, for each time someone logged in the past, for example, if that's what we're predicting, if that's the granularity of our predictions, what was the feature's value at that point in time in the past? And that allows you to easily generate a training data set that doesn't have any label leakage, it doesn't have any bad feature leakage, and so you can easily create high quality training data sets without a lot of the data science complexity that usually comes along with that.
Yeah, that's great. So the feature store concept itself is fairly new, right? So there's a couple of players in the field. Tecton is one, and I think Amazon has like SageMaker, Databricks has one. What is like the common components of a feature store that you see and that everyone agrees on? I'm sure everyone has their own value proposition, but what makes a feature store that everyone agrees on?
Yeah, so the core thing that everyone agrees on is that there's an online and offline serving layer. And so, this is a new category. It's actually, most things in the machine learning, in like the ML ops world and the ML ops stack, it's very fresh. And so a lot of different teams are figuring out exactly what is the scope, what are the boundaries of a specific product. We kind of developed our feature store in Uber, and we coined the term feature store, and we've been working on feature stores for a long time. So we're pretty confident about like Tecton's kind of geometry. But if you look across every product that uses the term feature store, what they have in common is they have a way to retrieve features quickly and at low latency for an online prediction, and they have ways to get historical data from an offline storage layer. And that's kind of the crux of the feature store, is managing that kind of data duplication across these different types of data infrastructure.
So a feature store kind of like connects various systems across your company, right? So your model might be really critical for your business. You might have an SLA that says, we never want this model to be down, but it also has dependencies on upstream systems. Like maybe there's a database that does not have the same guarantees that it's going to be up all time. Maybe it's going to be down every Sunday for patch or an upgrade or something. So how do you tie in the availability of your models with upstream systems that actually have the data somewhere?
Yeah, so that's part of the feature store's goal, is to provide an abstraction for the data scientist to hide that complexity of the upstream data infrastructure. So when a feature is defined in a feature store, that's when you address some of that complexity and you say, how often should this feature be recomputed, and where is this feature coming from, and some of the other details about how you can access this feature depending on the context. But then after that feature is registered in the feature store, it should look like, to the person who's using the feature store, just like any other feature. So it doesn't matter if this is a real-time computed feature, a streaming feature, or a batch feature. They're all just productionized features available within this common machine learning focused catalog that I can use to build an offline data set, or I can depend a production model on. And so that kind of standardization, or that abstraction, enables that kind of standardized consumption of these data, and that's a lot, that hides a lot of the complexity and speeds up the data scientists in a pretty significant way.
Mm-hmm. Let's talk a little bit about the compliance aspects and data governance aspects of it. A lot of companies, especially large ones, they have huge implications if you don't actually follow some of the data governance standards. Maybe a user comes back and says, hey, under GDPR or California privacy laws, I want this data to be deleted about me. How does that flow through this entire pipeline of systems that you have, where it may impact the predictions that you can do, it may impact, my experience? How does this tie in together?
Yeah, there's two approaches, right? One approach is to build specific capabilities for every single type of regulation. And what that means practically is build specific capabilities for like very common, prominent pieces of regulation. And the second is to make knowledge management much easier here. And that second approach is the thing that is the easier one to take on, and that's where we are, and basically, frankly, where most of the feature store industry is right now. Is about tracking metadata. So it's like we give you the capability to tag different data resources with, hey, this contains PII, this is sensitive data, this is how this data should be treated, this is the policy that is associated with this upstream data set, and the feature store ensures that downstream data sets are similarly tagged according to those policies, and it leaves it up to the consumer or the data team to make sure that those data are being handled appropriately, right? It's not like the actions are not being taken within the feature store, but at least the knowledge is being conveyed accurately. But there's more that a feature store can do, like, for example, providing a GDPR deletion API. So there's a variety of GDPR deletion requests. Can the data scientist build a way to automatically, this is part of like the maintenance of a data pipeline for ML, automatically handle the GDPR requests for their ML pipelines as well? And what does that mean? Okay, user X needs to be deleted. Well, we need to wipe them from all historical training data. We need to wipe their features from the online feature store. We just got to basically purge them from the system. And that introduces a lot of yet unsolved machine learning challenges, because if I train my model on this data set and now we've deleted an item from there, can my model be retrained now? Right? And what is the implication on my model if it cannot be exactly retrained because we're not allowed to have that data anymore? How do I, when I go to retrain my model, how do I generate that training data set? A lot of these questions are handled on an ad hoc basis right now, and we're working with our customers to build in the right kind of patterns out of the box to solve this stuff for them.
That's great to hear. I wanted to start wrapping up. Can you talk about what's in the future for feature stores? This is such a new thing right now, so I'm sure there's going to be a lot of change. What do you think is going to be the future of feature stores?
Yeah, I think the future for feature stores, the immediate future, is to continue growing, frankly. We have a lot of people are just learning about feature stores today, but feature stores have been in use for years at some of the top ML companies in the world, all of the top tech companies that you can imagine. And so what's next for us and for feature stores generally is to just education, just making sure people understand what feature stores are and making that as simple as possible for people to adopt. Some really cool things that our customers have asked us for that are likely coming next. Some interesting things are, for example, one, how do I automatically create great features from my data? Can we like auto featureize upstream data? Secondly, is can I have features in my models that do not come from my data, but come from someone else's data? So maybe there can be some third-party features that provide some context, like some really important things for the Uber Eats models that we were talking about before, is like, what's the weather and what is the traffic outside? Maybe that would be really great for me to use those features in my model out of the box, right? And that's something that kind of like a notion of a feature marketplace could be really useful in a feature store. What's next for us is just keep on working with our different customers. There's still a lot to build. There's a lot to do to support additional use cases. There's a huge variety of requirements across ML use cases, but then there's some of these like really interesting kind of like next generation things that can expand the value propositions of feature stores. I just mentioned a few of them, but some other announcements will be coming out soon.
Well, it's been great talking to you, Mike. Thank you for coming on the show.
Akshay, thank you so much.
This is Akshay Manchale for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.